Hello everyone, my name is Dan the Tutor. This is a clip from one of my weekly group tutoring sessions at the University of Delaware for Physics 201. If you have any questions, please leave them in the comments below. Thank you and enjoy.
Let's move on to work and energy. If you remember what I said earlier about work and energy, I said a couple things. Number one, I said that these two topics are often related, which is true. The second thing I said is we're talking about point 1 to point 2. So for instance, if this is kind of a weird example. You're not going to look at it until maybe the end of the course. But if I have, let's say, a rocket ship and I am launching the rocket into outer space, point 1 is on the surface of the Earth, point 2 is once we're in outer space. We're talking about two different points in time. Again, this example is not going to show up on your test tomorrow, but this is just to get the gist of what's going on here. We're looking at 2 points in time. And the cool thing is, with work and energy, I don't care what the object is doing in the middle. I don't care if the object makes a loop-de-loop on the way into outer space. I don't care if it takes the long way around and goes around the entire Earth before going into outer space. Work and energy says, as long as my energy is conserved, which I'll say what that means in a second, but as long as my energy is conserved, literally the path doesn't matter. I can take any path I want to go to outer space. It's going to be the same equation, essentially. Very cool. So now let's talk about work and energy. Let's start with work. The equation for work, hopefully you know this, again, I would have this on the front page of your paper, is work, which is W, equals a force times a distance, and then you often see times cosine theta. Now, you only have to worry about cosine theta if they give you an angle, or if it's friction, because, well, friction's always going to be an angle of 180, and we'll talk about that later today. But first, I do want to just say, work equals force times distance times cosine theta. This angle theta is the angle between force and distance. And again, we'll look at some example problems later today. But theta is the angle between force and distance. That's it for work. There's one more equation with work, but before we talk about it, we now need to talk about energy, the equations associated with energy. There are three kinds of energy that you care about in this class. 1, gravitational potential energy, U sub G. Hopefully you all know this. It's mgh. Then we have kinetic energy, K. That's going to equal 1/2 mv squared. Probably the most famous equation in all of physics, in my opinion, right here. And then the last one, the least important, is potential energy stored in a spring. That's going to be 1/2 kx squared, where k is the spring constant. A lot of people forget that. K is the spring constant. And that is going to have units of newtons per meter. Those are the units. So if you ever see units of newtons per meter in the problem, you know that's k. You know it's the spring constant. And then x here is the distance it's stretched or compressed. And they'll tell you that in the problem, most likely. So these are the three kinds of energy. Now, what can we do with this? Well, we can do some pretty cool stuff. The first thing you need to know is that E total, the total energy in your system, is equal to the gravitational potential energy, UG, plus the kinetic energy, plus the spring potential energy. Keep in mind, you can have 1, 2, or all 3 of these kinds of energies at any point in your problem. The trick is knowing when to use each one, which again we'll talk about. And then the second to last thing I want to say about this with energy is we do have a very nice equation for energy. It's E total at point 1 is equal to E total at point 2. There are many different equations that you may have seen in this class. Like for instance, sometimes professors teach it this way. They'll teach it delta U plus delta K equals 0. Personally, I hate this equation for several reasons. Number 1, I always hate delta notation. Number 2, I think this is way easier to understand. We're saying that the total energy at point 1 is equal to the total energy at point 2. This is also known as conservation of energy. Conservation of energy. What does that mean? That's a rhetorical question, I'm going to tell you. So conservation of energy, as far as you're concerned, means that there's no friction or outside forces. There's no friction or outside forces. In other words, if there's a pushing force going on, energy is not conserved. If there's air resistance, energy is not conserved. If you're pulling a box connected to a rope, energy is not conserved. The only time energy is conserved if it's just forces like gravity or normal force or even spring forces. Those are all conservative forces. Again, we're going to be looking at some examples today, but the biggest one right here is friction. If you have friction, it's not conservative. If you have friction, it's not conservative. So what does that mean? So we just talked about what we do if energy is conserved. That's all fine and good. But what if energy is not conserved? What if we have friction? What if we have that pushing or pulling force? What if we have air resistance? Here's what we do instead. It's a slightly modified equation, but very annoying. Everyone hates it. E total 1, the energy at point 1, plus the work done on the object, is equal to E total at point 2. In other words, the initial energy plus the change, because that's what work is, it's a change in energy, is equal to the final. And that's what this equation is really saying. Now again, work, we know what work is. Work is defined as force times distance times cosine theta, right? So the most common work equation or non-conservative force is friction. So I'm going to make a note. For friction, work equals negative force of friction, which I'll call Fk, times my distance. Why negative? Great question. So let's say I have a box right here that's moving to the right. And if the box is moving to the right, think about this. Which way will friction point? Well, friction always opposes motion, so friction will point to the left, right? And think about this now. What is my angle theta between distance and my force? Look at this. That's a 180 degree angle. Does anyone know the cosine of 180 degrees? If you guessed -1, you're a genius, because that's exactly right. So cosine of 180 is -1. I'm telling you, friction is always going to be negative Fk times d. Always. As long as you have friction. Okay. So that's pretty much it for all the equations we have. Now let's do a couple of examples so that you can be masters of physics.
Don't forget to like and subscribe. If you want me to start doing free weekly group sessions at your university, please post in the comments below or email me at dan@danthetutor.com. Thanks everyone. Bye-bye.